G'day Shri, welcome to my video project task 3, Structural Analysis CIVE 1188. Right, so just going over, so this is our cover page and this is my student declaration. So just moving on, just my table of contents here going over the assignment. Task 3 marking guide, which will be followed as law. Right, an introduction. So, why have I chosen this structure? So, first of all, just to go over the structure. So we've got a service center here. It's basically mechanics. And we've got a cantilever roof going off the top here, 3 meters high. And why have I chosen this one specifically? So this is a very unique structure for the area that it's in, Caulfield. You don't see a huge amount of these sort of structures. But when I was a kid, there's a tram line that goes across the road right here. And I would see this structure every single day on my way home from school. So I would look at it, and it would fascinate me because I didn't understand how cantilevers work, how this could just be quote unquote floating in air. But as I grew up and my understanding of science and my understanding of structural engineering grew, that uneasy feeling I had as a kid went away, and it was almost kind of like the origins of one of the interests in my structural engineering. Yeah, so just moving on. So we've taken a column here at 800 millimeters wide, column here fixed at the base and fixed here, and we've got an I-beam here and another I-beam here. And we'll be talking about these I-beams in greater detail later on in the deflection calculations. Right. So we've idealized the structure. We're just taking the side here. So we've got the fixed support down below. Right, so loading table. Now it was unclear, and I understand just with COVID going on and everything, the sheer number of emails he had, it was very unclear on how to apply loading in this assignment. So I took a little initiative. So I've applied, but physics being physics, I've applied load how I saw fit. So roof sheeting. I've added, so I've dipped on my knowledge from steel structures, and I've taken the LISAT bond guide, and I've worked out from the roof sheeting on top of the structure that was laying here. I've worked out the area, distributed it onto one of the beams, and then I've plussed on my student number as a variable, and then I've said the building itself is applying load onto this little corner here as well. So I've added all these loads together, and you can see the loads applied here. I've then split these two structures into two substructures. So as you can see, here's a little cross section of the concrete beam here, 800 by 800. And then this here is the beam that we were able to work out doing our deflection calculations. We'll talk about this a little bit more in depth, but it's an I-beam that needed to span 3.1 meters. Right, so moving on, we've got our substructure 1 and 2 idealized here. So we've just got our loading seeing fixed here and fixed here at both bases. Right, so our calculations. So from substructure 1, we've worked out our reactions, very basic. I've just dipped on my knowledge I've worked out from physics and TAFE to work these ones out. And then working out our shear force and bending moment equations. And then from here, we know that we can say sub in a value of x and punch out our shear force value between our limitations here, punch in a value of x and work out our moment from the limitations of 0 between 1 and 3. The process is repeated again for substructure 2. Repeated again, and we're left with our values. We've taken these values and then we've subbed them into our shear force and bending moment diagrams. So from the shear force and bending moment diagrams, very basic, we've got a composite of both substructure 1 and 2, but we can see down below here that most of our bending moment is going to be from substructure 2. Now, this is where I had to use a little initiative, because from this, from just a general physics point of view, you would think, oh, well, substructure 2 is now what we're going to analyze. But no, we know that there's going to be more load on substructure 1. Therefore, I've chosen to work out both substructure 1 and 2 so I can compare, as opposed to just working out substructure 2 as would be fit in this case. Right, so moving on. So our deflection calculations from substructure 1 and 2. So first of all, we've got our slope calculations. So we've got our slope calculation here, so it's just a single integration, a deflection calculation with a double integration, and then we're left with our unknowns here. Right, so now we had to work out what are the details we're going to sub into these calculations. So we know our modulus elasticity is still standard, 200,000 MPa. And then I had to trial 4 to 5 different beams from the hot rolled steel catalog from one steel. So this is dipping again on my steel structures knowledge. I've trialed out 4 or 5 into these calculations and found that the most appropriate beam for dimensions, weight, cost effect, and what they would have used is the 530 UB 92.4. So because of that, we don't need to work out our I because it's given to us. So that's given to us here. Worked out our X, and then we fire these values into our calculation just from the new structures course, and then we get our answers. Process is repeated here, except of course slightly different, of course. Slightly different there. Sorry, that was our total length rather. So yeah, slightly different calculation to find I, because it's just very basic, 800 times 800. And we've got a different modulus of elasticity, of course, because we're using a different material, high strength concrete. So this is the reason I've done both equations, working out substructure 1 and 2, because we can already see that substructure 1 is going to be vastly different from substructure 2, and is probably going to be the one that, because a 800 by 800 wide concrete column isn't going to incur much stress compared to an I-beam that's encountering 10 plus 10 kilonewtons of UDL. So we've worked out both of these, and then moving on. Right, bending stress calculations. So what can we see here? Substructure 1 vastly different to substructure 2. Crazy differences here. So we've worked out, we've taken our values M, taken our Y, distance from the neutral axis. We've subbed in our I's, so in this case from our hot roll, our I that we've worked out previously on the previous page, subbed them in, got both of our values. Very crazy differences here. So not much difference going, not much action going on with the concrete, but lots of action going on with the steel. So our shear stress calculations. So we're just working, the big key variable in these two situations is just basically finding out our centroids from that neutral axis here. Worked out our Y here, worked out our A here. This being a column, this being an I-beam, they're going to have vastly different calculations. And then from here, we sub in our values. Values are subbed in, and then yeah, we've got our max stress down here, max shear stress. Rightio, moving on. And we can see max shear stress in substructure 1 is going to be vastly more than in substructure 2. In plane principal stress, right, so we already know that the substructure 1 is going to have way more craziness, way more stuff going on. So we're mainly just focusing on that. We're saying that our the shear, the XY is taking that as 0, and then so we've got our 0 here. We're saying that basically our structure is stationary. It's not moving to place. It's not tilted 30 degrees. It's not tilted anything. 0. So we're saying. We're saying that, but our answers, and well, yeah. So we're just saying it's regular. So between 0 and 90 is our answers for this. This is just what you get from any basic non-crazy equation. And then plug in find in our values at the end here for our principal. For our in-plane principal stress. We've already worked out our max orientation between 0 and 90, and then fired that out. Stress 1, 23.544 and 0. Right, so To finish it off, the principal stress, shear stress calculations. What a mouthful. The max in-plane shear stress, in other words. So we're taking our stress about X, stress about Y is 0, and then we're going to take, in this case, we're taking our max stress here, and we're using substructure 1, because even though if we went back to the start, they'd want us to use that substructure 2, but substructure 1, clearly more action going on. So back here, we're going to plug in our value from there, fire that out, and then we know that's our max right here. And then orientation, work out our orientation, plug in the values, 0, therefore 45 degrees. All good. And then our conclusion. Right, so our conclusion, basically, I'm just going over why I found it interesting, what was interesting about the deflection that was found, I've gone over basically already about what I found interesting about the bending stress, the disparity, the fact that I've worked out both calculations, not just one, going on. So, and then with our and basically all in all, it was a great experience. It was challenging, very rewarding, and my childhood self would thank me, because now I know if I stand on here, what's going to happen. I know what's going to happen. So moving on, just my appendix going over task 3. So this is where we idealize the structure as frame. Very basic, so it's all included here to be gone over. Task 1, just the structure. And then we've got just the details in the approval letter. Alright, thank you, Shree. I appreciate it.